Problem 11 on critical radius of insulation of cylinder. An electric cable of 20 mm diameter is insulated with rubber which is exposed to atmosphere at 30 degrees Celsius. Calculate the most economical thickness of the rubber insulation when the cable surface temperature with or without insulation is at 70 degrees Celsius. Also calculate the percentage increase in dissipation and current carrying capacity when most economical insulation thickness is provided. Take K thermal conductivity of rubber as 0.175 watt per meter Kelvin and convective heat transfer coefficient H 9.3 watt per meter square Kelvin. So in order to solve this problem, let us first draw the schematic. So in this problem, initially there is an electrical cable without insulation. I would call this as bare electric cable, and it is directly exposed to the atmosphere. Atmospheric air will have air. Atmospheric air having convective heat transfer coefficient H infinity O and its surface temperature T infinity O. Let's say surface temperature of this electrical cable is T. Electrical cable carries current I1 initially and its electrical resistance is Re. So by virtue of this electrical current I1 which is flowing through this electrical cable, heat will be generated at the rate of I1 square Re, and under steady state condition this heat generated will be dissipated at the same rate to the environment. Let's say at the rate Q1. So this heat dissipated is equal to heat generated Q1. Now in second case, the same electrical cable is provided with rubber insulation having thermal conductivity K. It is exposed to the same environment having temperature T infinity O and convective heat transfer coefficient H infinity O. Let's say in this case it is carrying the current I2 and its electrical resistance will remain same I. So this will generate the heat at the rate of I2 square Re, and this generated heat will be dissipated to the environment at the same rate by virtue of steady state heat transfer. So this rate is Q2. Let's say surface radius of this bare cable is R1 and radius of the rubber insulation is R2. So this way I could draw the schematic representing all the important parameters involved. Now let us draw the equivalent electrical circuit for this. So in case 1, the flow quantity will be heat transfer or heat dissipation rate Q1 and thermal resistance will be offered between the surface temperature of the cable T and air temperature T infinity O, and this thermal resistance will be by convection only, and finally heat will be dissipated. In the second case, heat will be transferred from surface of the cable to the insulation by conduction and from outer surface of the insulation cable to the air by convection. It is mentioned in the problem Surface temperature of the cable is not going to change, so it will remain small t. Let's say outer surface temperature of insulation cable is T1 and air temperature is T infinity. Now equivalent electrical circuit. So flow quantity will be Q2. The first thermal resistance will be offered between temperature T and T1 by insulation, and it will be conductive thermal resistance. And second thermal resistance will be offered by air film between temperatures T1 and T infinity O, and it will be convective thermal resistance, and heat will finally dissipated to the environment. These two thermal, the convective thermal resistance in this case will be RT infinity 1, and this will be RT infinity 2. Both will be different. Now after drawing the schematic and equivalent electrical circuit, let us enlist all the things. So as you can see here, in the problem, diameter of the electrical cable is 20 mm, outer temperature 30 degrees Celsius, and surface temperature with and without insulation is 70 degrees Celsius. And K and H properties are given. So diameter of electrical cable is 20 mm, so its radius will be 10 mm, 0.01 mm. Surface temperature of cable 70 degrees Celsius. Outer surface temperature of air is 30 degrees Celsius. Thermal conductivity of rubber insulation is 0.175 watt per meter Kelvin, and convective heat transfer coefficient of surrounding air is given as 9.3 watt per meter square Kelvin. In order to solve this problem, we need to make some assumptions. So assumption number 1 is one dimensional steady state heat transfer. Assumption number 2, homogeneous and isotropic material. So K and H values will be constant. Assumption number 3 will be heat transfer in radial direction only. And and unit length of electrical cable is considered, that is L is equal to 1 meter. What happens? Electrical cables length can be anything from few meter to few kilometer. So for this particular analysis, I am considering the length of the electrical cable as unity. So entire analysis will be applicable to the unit length of the electrical cable only. In this, we cannot make the assumption no heat generation, because there is a heat generation. What is happening when current I is flowing through electrical cable of resistance Re? Heat is generated I square Re. So I cannot make that assumption here. Now fourth one is find out. So the very first thing we are supposed to find out, percentage increase in heat dissipation. So it is nothing but Q2 minus Q1 over Q1 into 100. So this thing we are supposed to find out. Similarly, we are supposed to find out percentage increase in current carrying capacity, that is I2 minus I1 over I1. So these three These two things we are supposed to find out. Now let us do one more thing. This is second thing. This is third thing. The very first thing we are supposed to find out is economical thickness. And this economical thickness is nothing but R2 is equal to RC, that is critical radius of insulation. Now let us do the detailed calculations. So let us first find out so the problem is asking to calculate most economical thickness. So with regard to the heat transfer, this is nothing but critical radius of insulation for cable. And this critical radius of insulation is required for maximum heat transfer. So since cable is of cylindrical shape, so critical radius of insulation will be K over H infinity O, where K is the thermal conductivity of the rubber insulation, 0.175 over 9.3. So it comes 0.018817 meter, or RC will be 18.82 mm. So this is critical radius of insulation. We have been asked to calculate the most economical thickness or critical thickness of insulation. So this is nothing but CRI, critical radius of insulation. What will be critical thickness of insulation? CTI will be RC minus R1. 18.82 minus 10. So CTI comes out 8.82 mm. So this is the required answer actually. So part 1 is over. Now part 2. In order to calculate part 2, we have to calculate Q2 and Q1, where Q1 is rate of heat transfer when bare cable is considered. Now as we can see here, when this bare cable is directly exposed to the air, heat transfer will take place by convection only. No other mode of heat transfer will be there. So under one-dimensional steady state heat transfer from Newton's law of cooling, since convection mode of heat transfer is there, so Newton's law of cooling will be coming into picture to calculate Q1, and this will be H infinity O into area, surface area of cable into T minus T infinity O. Putting the values, H infinity O is 9.3, area of cable 2 pi RL. I can sum up here. So 2 pi, radius is 0.01, and length I am considering unity, T is 70 degrees Celsius, and T infinity O is 30. So heat dissipation rate from the bare cable per unit length comes out 23.37 watt per meter. Now in second case, let us find out Q2, that is when insulated cable is considered. So under this condition, under one-dimensional steady state heat transfer, now let us refer the schematic. From bare cable through this insulating material, heat transfer will take place by conduction, and from outer surface of the insulation to the surrounding air will be by convection. So two mode of heat transfer will coming into picture. And in the second case, the radius of thickness is considered as most economical thickness. R2 is equal to RC, that is 18.1882 mm. So Q2 will be the heat transfer from cable to insulation will be equal to rate of heat transfer from insulation to air. Now in terms of temperature difference, I can write them as T minus T1 over RT is equal to T1 minus T infinity O RT infinity O. Individual, once again I can use either of the equation to calculate rate of heat dissipation. In second case, that is Q2, provided the value of T1 is known to me. But in our case, the value of only T and T infinity O is given. So let us rewrite the equation for Q2 in terms of T and T infinity O. So under such condition, thermal resistances will get add up. Now here RT is conductive thermal resistance of rubber insulation, isn't it? And this is of cylindrical shape. So how can I calculate this? 1 over 2 pi KL log of RC over R1. Since I have considered the radius of insulation as critical radius of insulation. So this I can calculate as 1 over 2 into 0.175 into L. Log of RC is 18.82 over 10. So this value comes out. So here pi is also there. So RT value comes out 0.575 degrees Celsius, sorry, Kelvin per watt per meter. Then RT infinity O is convective thermal resistance of surrounding air, and it can be calculated as 1 over H infinity O into AO. So this can be written as H infinity O into 2 pi RC into L. So RT infinity O, after putting the value, H infinity O is 9.3, 2 pi L, and value of RC is 0.01882. So this RT infinity O comes out 0.909 Kelvin per watt meter. Here L I have not considered, so this will come out for L. Therefore, from equation 3, Q2 will be T minus T infinity O, that is 70 minus 30 over 0.575 plus 0.909. L is common. I can take it in this. So Q2 by L comes out 6.95 watt per meter. Now I have the value of Q1, 23.37. I have the value of Q2 per meter length. Now I can calculate percentage increase in heat transfer, that is Q2 minus Q1 over Q1 into 100, that is 26.95 minus 23.73 over 23.73. So this comes out 15.30. So this is the required answer. Answer number 2. Now let us calculate point number 3, that is percentage increase in current. Okay, so we have this Q1 is equal to IN square RE. So I1 will be equal to Q1 over RE whole square root. Similarly, we have Q2 is equal to I2 square RE. So I2 will be Q2 over RE whole square root. So we could express the current carrying capacity in terms of heat dissipation rate. Therefore, I2 minus I1 over I1 into 100 will be, I am directly writing, RE is cancelled, RE is common, so it will be cancelled everywhere. It will be square root of Q2 minus square root of Q1 over square root of Q1, that is square root of 26.95 minus square root of 23.73 over square root of 23.73 into 100. So this comes out, let me calculate this, 6.56%. I2 minus I1 over I1 into 100. So this is the percent increase in current capacity, current carrying capacity. So we can sum up at the end. Critical radius of insulation is 18.82 mm. Critical thickness of insulation is 8.82 mm. Percentage increase in percent carrying capacity is 15.30%, and increase in current carrying capacity is 6.56%. So with this, we could solve the numerical.